Yesterday, I said we wanted to take a closer look at the universal notion of computation. And I said that the one concept that ties everything together, as far as understanding where the prover-verifier model fits, is the notion of reduction. We saw a reduction yesterday from exact cover to knapsack. Today, we will see one more. And then we're going to wrap this first part after getting just a glimpse of where the seed out of which this prover model verifier grew. So the important point is that we're dealing with this notion of a reduction, and it's the notion that is hopefully will tie everything together basically throughout the whole series. Today we'll start with the satisfiability problem, or SAT, as it's called for short. So we call a variable that can assume values of 0 or 1, we call it a Boolean variable. So x here is a Boolean variable. It can assume one of these two values. We use this symbol to represent or disjunction, and we use this for and we use this for negation, not. So negation is just logical complement. It just flips everything. You're probably familiar with these truth tables. So or is false only if both are false, and is true only if both are true. And of course, the negation is just a flip. Just to note that order doesn't matter with ands and ors. In other words, ands and ors are commutative and associative. Basically, x1 or x2 is effectively the same as x2 or x1, and so on. So order doesn't matter. And also when you have three variables, so x1 operator, whether it's and or, x2 or x3 is also the same thing as, say, x1 parentheses x2, here is an or, x2 or x3. So order doesn't matter when you're evaluating these truth tables, basically. So x here, we are defining the three-set satisfiability problem now. When we're defining a problem, we introduce a bunch of elements and then followed by a question. So x is a set of variables, Boolean variables, n of them, and their negation, each variable and its negation. S is a Boolean formula. It's a conjunction of clauses, meaning it's a bunch of clauses joined together by an and each clause has three variables. In the satisfiability variant that we are dealing with today, it's a three sat, means three variables. Each clause in S is a disjunction of three variables, three Boolean variables. And the question is, here's our question, here's our problem. Is there a 0-1 assignment to X variables that makes S overall evaluates to 1 or to true, if 0 and 1 represent true or false to you, basically. So we are looking for a way to assign each variable a 0 or a 1, such that when we plug them into each clause, the overall S formula evaluates to 1. So here's an example. This is an S formula, and it has three clauses. These clauses, disjunctive clauses, and they are connected with an and, so we call S conjunctive formula. So what should x1 be, and x2 and x3 Should we give it 0 or 1? And as a result, its negation, if you give x1 0, then that means its negation must be 1, etc., such that the whole thing evaluates to 1. There could, of course, be more than one satisfying assignment. It is possible. So here, for example, if you try, let's say, x1 is equal to 1, x2 is equal to 1, and x3 equals to 0, you will notice that every clause satisfies. This one obviously satisfies because you only need one of the variables to be 1 for the whole clause to be true. So this one is true because of x1. This one is true because of x2 right away. And this one is true because of x3. If you flip it, because x3 is 0. But it's also true because of x1 as well. There could be more than one assignment. So this is a satisfying assignment. It's a solution to our problem. So if someone gave you this assignment, you just plug it in and you say, oh yeah, you're telling the truth. It's true. But imagine you have large instances. Imagine thousands of variables, millions of clauses. What are you going to do? In general, actually, when we're talking about this problem, always keep in mind infinite number of possible instances. What do you do? What is your instinct? It's not really clear how we would go about it to solve it quickly, if you think about it. What are you going to do? There are, of course, heuristics that speed up termination, but none of them guarantees the optimal solution will always be like found. And we're talking here, as I emphasized yesterday, we are talking about 100% satisfying solution. So we're not talking about a solution where 99% of the clauses are satisfiable except one pesky one. We want everything, 100%. We want all of them to be satisfiable. And number two, we want a strategy that works regardless of how the instance looks like, how the structure of the instance looks like. So yeah, this is one of the hard problems that if you stare at it, and people have been staring at it for decades, you will see that you cannot find an algorithm, or no one has ever found an algorithm that is guaranteed, like proven to always find the correct solution quickly, easily. If we have n variables and each can assume two values, 0 to 1, then there are, of course, 2 to the power n possible combination, right? Of course, this is an exponential, like search space. It's massive, it's huge, this one. So for relatively reasonable amount of n, your search space might be larger than the number of atoms in the universe. And as I said, we can, use heuristics to pick forks in the road. But as we saw with the problems that we saw yesterday, we could start trying the tree. So here's x1. We'll say, okay, we'll start with x1. Should we give it a 1 or a 0? We will, try to make a smart choice, and then we're going to say, okay, for x1 we're gonna go with 1. So now we're going to look at x2. That's our next variable, assuming that x1 is true, is false, is 0, and then we're gonna for x equals 0, x2 will also be presented by two choices. It is 0 or 1, and for each one will lead it somewhere down the path. So the intriguing fact, is that if someone gave you an assignment, even if you have, let's say, 1 million of variables, like this have 1 billion variables, if someone claimed that they have an assignment, plugging it seems to be really easy. Like there seems to be an asymmetry between search, which we are really stuck with this naive thing, try everything, get stuck. Like if you follow this path, we might reach xn, and whatever choice we put for it, 0 or 1, the overall formula is not satisfiable. So we find ourselves backtracking again and trying something else. But again, the intriguing fact is that if someone did actually find the solution, then verifying it is easy. You just plug it into the formula. Now, let's consider another problem. This will be our second and last problem. We will come back shortly to satisfiability, but first, let's look at this other problem. It's the 3 coloring problem, and the question is there a way to color the vertices of the graph with blue, green, or red? Yeah, we can agree that this is red, such that no 2 adjacent vertices have the same color. Okay, we want to assign a color to each vertex, one of the 3 colors, such that neighboring vertices do not share the same color. They do not touch it. They do not have the same color if there is an edge between them. Note that the graph is undirected. Okay? So for example, this is an invalid coloring because, well, these 2, they have an edge between them and they share the same color. Same thing for this one. So this is not a valid coloring, for example. This one is problematic because it's neighboring with the same color with two vertices. But this is a valid coloring. So you look at the graph and each vertex has a different color from every neighbor that is connected to. So this is a valid coloring. So what's the strategy when we have very large graphs, right? So, imagine this is, you can think of this graph as, planets and stars and everything in the universe that exist in some physics simulation. So obviously there is a massive number of them. And suppose that one of the problems that they're dealing with in physics relies on this fact. It may not be because physicists wants to color the universe, but because some other question is equivalent to this 3-color problem, just like we saw yesterday. Remember yesterday we reduced from exact cover to knapsack. Sometimes we are using the 3-coloring problem, but semantically we are translating the solution to something else. So this graph may very well be, genes or stars or whatever. So imagine extremely large graphs. What do you do? This is indeed, again, one of those problems where if you stare at it, and I encourage you to, you might have some heuristics. You'll say, I'll try this. And let's think about one instinct, for example. So you could say, okay, I'm going to start coloring islands first. So you notice that your graph has lots of islands, So I'm going to start coloring those, independently. And then I'm going to start trying to plug the islands together. The issue is everything might work until the last annoying island, which, although it was colored correctly in isolation, you couldn't find a way to connect it to the rest of the graph without violating the constraint. So you try a different coloring for that one item, which fixes the problem. Except that now that island has a conflict with another, and so on. So that very, very last island that, the whole graph is colored now, except that last annoying one, you might find yourself, it's very possible that you will have to undo everything you did because you could not plug it into the graph. So imagine if it's this island, for example, and you're trying to plug it here, but its neighbor has the same color. But if you change this one, you have to change the other one, and then so on. So it's like it metastasizes, and it causes you to backtrack here, backtrack all the way to beginning. There is no guarantee, basically, that this instinct will lead you to the absolute optimal solution. Another instinct you might have is you say, I'll start with highly connected vertices that has so many edges, because these are more likely to be problematic. They have more neighbors, therefore they are the ones that will be responsible for conflict. So you color those like highly connected vertices, and you color their vicinities, and you move to the next highly connected vertex, and so on. This actually does pretty well in finding approximate solutions in practice. But again, if you insist on finding coloring of all vertices, you're not satisfied with 99% coloring. There is, once again, no guarantee that you will get stuck at the very, very end and come back, roll back what you have done and try a different path. So this should be familiar by now. Again, we are dealing with exactly the same thing here. We start somewhere. There's the first vertex, give it red VI. We'll start with VI. Say we are following the highly connected node. And then you say, okay, for which node should I color next? So you pick, let's say, VJ, and you say, okay, this is the next vertex that I'm going to color, VJ, and I'm going to give it green. And then from VJ, you have so many choices. Okay, so you pick one based on some heuristics, VK, and you say, okay, that one is blue, and then you go from there again, and so on. So again, you might reach the final node, and you have no way of coloring that node without violating something. So you go back either here and try something else there, or go all the way back and try something else here. Try this one, for example, and so on. So again, the three coloring problem seems to be the same at heart as satisfiability, and indeed as the problems that we saw yesterday. And today we're going to prove it. So today we're going to reduce satisfiability into coloring, right? We're going to take an instance of, well, first we'll take an instant, but you know, we will see also the generalized reduction. We're going to take it, and we're going to construct a three coloring instance that is solvable if and only if the original S is satisfiable. So let's reduce by example. This is the example set instance that we saw earlier. It has three variables and three clauses. So if you think about it, what makes a satisfiability formula, what makes a SAT formula satisfiable? It's basically two things. All variables are either 0 or 1. Okay, so we are not allowed to leave a variable out. Every variable must be assigned either 0 or a 1. And all the clauses must evaluate to 1. So here in this clause, at least one of the three has to be a 1. At least one of these three has to be a 1. Well, x1 should be 0. If x1 is 0, this will be satisfiable. But the point is, at least one of the variables should evaluate to 1. So it's a 1 if it's in normal form, or it's a 0 and if it's in negation form. So we are going to reconstruct a three coloring instance, okay, that is colorable if and only if these two conditions are met. If we can prove that these conditions are met in the three coloring instance, when translated back into the context of satisfiability, then the reduction is perfect. So let's start with condition 1 first and see how we can generate a graph and guarantee this property. We will think of green as 1, and we will think of red as 0. And blue, we will think of it as a spacer. It has no special meaning. It's just a spacer color. We begin constructing the graph by drawing this triangle. 3 vertices connected in this way. Now, this might seem, you might ask, where did this thing come from? Don't worry, it will come into the clear shortly. So far, so good. They are all adjacent. This is the seed of our graph, basically. They are all connected, and they all have the different colors. We are going to use this little nifty thing to enforce condition 1. We're going to use it to enforce that every variable is either 0 or 1. So how do we do that? We create a vertex for each variable in our formula, so x1 and its negation. Remember, the variable and its negation, they are two variables, and we connect them together. Okay, so this is, remember, we are building up a graph here. Yeah, we are building a graph bit by bit. So the fact that x1 is connected to its negation means if there is ever coloring of this graph that we are constructing, we're not done constructing it, but once we are done constructing it, if there is a valid coloring, x1 and its negation will have different colors. Okay, which they should. And we are going to connect all of them to the spacer. Now, what does these connection, what do they do? They enforce something. They enforce the fact that both x1 and its negation have either green or red. They cannot assume something else. They cannot assume the spacer, the blue. So they are all forced, all variables are forced to assume either a green or a red, which ourselves from the outside, we are semantically interpreting as 1 and 0 in the context of satisfiability. They are forced to assume green or red, and they are forced to be different. They cannot both be green, and cannot both be red because they have an edge between them. And the fact that they have an edge between them will prevent a valid coloring. Okay, so this takes care of our first condition. This graph is colorable if and only if each variable is either green or red, which we interpret as 1 and 0, and its negation is the opposite. Okay? These edges enforce the fact that they are either green or red, and these edges enforce the fact that they are opposite. They do not have the same color, each variable and its negation. So let's now add more components to the graph to satisfy the second condition, to ensure that all clauses evaluate to 1. So look at the first clause. Okay, we will build a gadget now to enforce this clause. To enforce what? To enforce that the clause overall evaluates to 1. Okay, this is a sort of an OR gadget that has x1, x2, and x3, because these are the variables in our clause, as input. Okay, as you can see, the overall gadget is a mirror of the smaller gadgets, basically. So you have the same gadgets connected to each other. We want to force the output here. We want to force this one to evaluate to 0 if all the input of the input of the clause are all 0, right? Because that's the only case in which a clause is false, is if all of them are 0 or false. It only takes one of them to be true. So we want to enforce this. We want to enforce the fact that the output node here is green, meaning 1, is red, 0, if and only if all of them are red. So if x1 and x2 and x3 of the first clause are all 0, the output node is forcibly 0. But wait, if all 3 are red and the output is forcibly red, we are guaranteed that the graph will never be colorable. If this graph, we'll see the details here shortly, but if this graph is, if this node is ever red, the graph overall is not colorable. Why? Because we created a connection to red. And the fact that there is a red here, an edge between a red and a red, means there is no coloring. So the clause is not satisfiable. So what if, or okay, let's take an example. Suppose x1 is green. Oops. X1 is green, and x2 and 3 are red. Okay. What can we color these nodes with, these two? Well, this one has to be, could be either, it could either be blue or green, and this one can be blue or green. So they have to be, we have blue and green. So we can say, okay, we'll put this one blue, or we'll put this one green, which means that this one must be red because it's their neighbors. And now let's look at this part. We have red and red. So this one could be green or blue. And this one could be green or blue. So again, we make a choice. So we'll say, okay, we'll make this one green. We'll make this one blue. So far we are satisfied, which means what?
Hey, Ali?
Yeah.
The neighbor to x1 should be red.
The neighbor of what? Sorry.
The vertex adjacent to x1 should be red, not green.
Oh, sorry about that. Yeah. Yeah, good point. Red. Okay. Which means this one must be green. Okay. So these two we have green and blue choices to pick from. So this one has to be blue now, and this one has to be green, which means what? We can see that we were forced into coloring this one red, but we can't color it red because this one is red. So it cannot be, it's not a valid coloring. It doesn't lead you to a valid coloring. So now let's suppose that all of them, x1, x2, and x3, they are all green. Okay, so this one and that one, we can pick between red and blue. So let's say this one is red, this one is blue, which means this one has to be green. This one and that one, these two, we need to color them now. So we have the option between red and blue. So let's say this one is blue, and now we have to force this one to be red, which means this is forcibly green, which it should, yeah. So the gadget forced this node to be green. If you switch between these two, you say this is blue and this is green, it will still be the same thing. The point is that we forced this node to be green because the input is green. One of the inputs is green. Finally, let's illustrate the important case in which all of them are red. So if all of them are red, what do we want here? We want this to be forcibly red. We want to force it into red. Because if it's red, then the graph does not have a coloring. And if the graph does not have a coloring, then the satisfiability formula, when translated back, is not satisfiable. We want to enforce that. So red, you have two inputs that are red. So these two have to be green and blue. So we can choose this one to be green. We can choose this one to be blue, for example. Here, this has to be red. There's no other choice. Okay, these two, we have two red inputs. So the only two choices is blue and green. So let's say we'll pick this one to be blue and this one to be green. This is the only choices we have. We can try green and blue, same thing. And that forces us, as you can see, there is, you cannot get around it. This forced this one to be red. Okay. There is no other way for this to be colored, to be colored anything different. And if it's red, by virtue of this connection, the graph is not colorable. So this takes care of the second condition. So you might ask, okay, where did this gadget come from? Like, you just dumped this thing on us. Like, where did you come up with it? What is the reasoning? What sort of reasoning did we use to construct this graph? It seems to be, you know, arbitrary. How did you come up with it? And the reality is, like, these reductions, there is an art to them. It's not completely science. There is a lot of intuition that goes into them. And the very first time that someone did a reduction, it was not obvious, and it took a leap of thought to come up with reductions like these. But once people saw these reductions, they started, you know, getting an intuition. So the answer is that this graph was constructed with a little bit of tinkering, a little bit of intuition. Yeah, so it's not completely science. It's kind of an art. There is no mathematical way of, you know, constructing a reduction, or coming up with a construction, reduction, basically. It takes some intuition. So yeah, the reduction is not a systematic science, but I hope that you can see how we satisfied both conditions. How these connections take care of the fact that each variable and its negation have different variables. These edges take care of the requirement that each variable is either green or red. It must assume that color, basically. And this gadget, as we saw, this gadget enforces that this node, output node, is green is green if at least one of the three is green, which we didn't go through every case, but I encourage you as an exercise later on to go over every case when X1 is green and the other two is green. I encourage you to do that. But what we went over in details is the case where all three were red. And we saw that when everything is red, this node was forcibly red. And that's what we want. So if a three coloring exists, we translate back. What do we translate back? What do we send back to the SAT people? We send them the colors of these variables. We say, in the valid graph that we found, these are the colors of the variables. And the SAT people will say, okay, perfect. X1 is green, so assign a 1 to it. X2 is red, assign a 0 to it, and so on. I abstracted the gadgets here in this triangle. You know, we will add a gadget for every clause. It's exactly the same thing. The black circle here, the black triangle is that gadget that we saw. It's this gadget abstracted away. So we will do exactly the same for each of the clauses. This is the clause gadget of the second clause, and you can see there is a connection between its variables, the negation of x1, x2, and the negation of x3. They're connected, and the output node, this should be one node. The output node here is again connected to, you should think of this as an output node. Here, same thing. There is an output node. They have two connections. Output nodes have two connections to blue and red, meaning the output of each clause must be green. It has to be green in any valid coloring. It cannot be anything else. And the same thing for x3. So the variables are x1. So let's connect x1 to it. The negation of x2, which is this one, and the negation of x3, which is that one. So we connect it here, and the output again, let me use orange. We will connect the output node once again to one to blue and one to red. And that's the final gadget. That's the final graph. This is an artificial graph that we constructed to correspond to this satisfiability formula. And although we did it for one example, satisfiability, you can see that it's really easy to generalize it. You can easily, a 15-year-old, a 12-year-old could easily describe systematically how to generate this graph given a satisfiability formula in the general form. So one other observation that this is the same as we had yesterday is that it's super easy. The reduction is super easy. It doesn't take much. It doesn't take any search or anything. Okay, so we saw 4 problems so far. Okay, we saw how to reduce one to the other. I encourage you later as a form of exercise to look into the reduction to them and to internalize them a little bit. But we also stirred up some dust along the way, because so far I have been saying, I've been throwing these things in the air. The reductions are easy. We get stuck. We backtrack. This problem is hard to find a solution for. So I have been throwing stuff in the air, kind of. And if you feel that there is a bit of dust in your brain because of what we have done so far, that is, don't blame yourself. We have indeed been stirring a bunch of stuff. We have been throwing things in the air without actually being super, super concrete about them, basically. But that's the point, really. I wanted us to get a sense, to get intuition, to start touching and feeling this notion of hard search. How do I find a satisfiable? How can I be smart? How can I come up with a smart way of solving it? And I want you to start feeling that difficulty of search and that easiness of verification. And more importantly, to see that how the reduction is easy, like going from one problem to the other is like super easy. It doesn't take any sophisticated search. The reduction itself could be very insightful. It took some intuition to come up with it, but once you have it, you can generalize it very easily. So, okay. We started with exact cover. Okay, and we saw how, despite the simplicity of the description, it doesn't seem to be solvable very quickly. We tried two instincts basically, and you could have other instincts, but at the end, we saw how that whatever you come up with at the end, you could have to go back all the way back. So the problem seems to be hard generally. We looked at the knapsack, same thing. We tried 2 instincts, which gave us decent solutions, but when we tried the exhaustive search, we've squeezed out one more value at the end. By the way, speaking of knapsack, you may, if you have used it before, because it's a very common problem, you may have heard that it has a pseudo polynomial solution, meaning it has in practice a very fast solution, which is true, but it's pseudo-polynomial, meaning it's only seemingly true in the practical cases, but in the infinite case, in the case where you try purely random instances, it becomes exponential again, because, well, the quick solution uses dynamic programming, which builds a table, and the dimension of the table depends on the capacity. And when you double the capacity, the size actually goes exponential. The size of the table is not linear in the input size. So this is just just a note in case you have heard that the knapsack is easy, which in practice it's very, very easy, but in the general case it's also exponential. Okay, we reduced exact cover to knapsack. And then today we looked at satisfiability and the coloring. I'm highlighting here the correspondence between the questions. And we said yesterday that these two are the same at heart. And today we showed that these two are the same at heart as well. But it should be obvious now that they are all the same as at heart. In all of them, we ended up doing this basically. So, okay, it turned out there are dozens, hundreds, thousands of these problems that can be reduced to each other. Okay. In fact, 3 coloring can be reduced to exact cover. Okay. Satisfiability can be reduced to knapsack via other problems. There is a path of reduction between the two. These are the problems that we saw yesterday and today. But there are many, many others. There are dozens, hundreds, thousands of these problems, and they are encountered routinely in every domain. These problems, what is the category of this problem? I haven't given them a name yet. Well, it's the problem that are the same at heart, and they seem to be hard to solve, but easy to verify. That's the common thing between them. And as I said, there are heuristics specific to each one of them, and it's specific to the type of instance. If the knapsack instance that you're dealing with is in the context of the Apple assembly line in China, the instances will have some certain structure that you can take advantage of. But here we're talking in the general case and in the mathematical sense. So you might be wondering, where is this going? What's going on? Okay. The bad news is these problems, we have not found a quick solution for them over the past 4 or 5 decades. They seem to be fundamentally hard. Okay. There is no algorithm, there's no null algorithm that will guarantee we don't get stuck at the very, very end and have to backtrack all the way to the beginning. This equivalency between them via reduction makes us less hopeful that an algorithm will be found, because the implication will be huge. But also the fact that thousands of people have been trying to solve different problems that are the same at heart, but we're not able to, makes us believe that there is something fundamental and unique about these problems. And indeed there is. But here's the good news. We do have AWS, and we also have Solana, of course, which is more powerful than AWS, which, we can use to solve our problems in practice. So what's a big deal? What's the big deal that these problems are intractable? Jeff Bezos has infinite money, and he's happy to lend us some compute in AWS. So this is a computer scientist, true depiction. And he says, I have problems. And Jeff Bezos says, I will solve them for you for $9.99. Just throw them at me, no problem. But that's not really the good news. The fact that we have Jeff Bezos is not the good news. The real good news is that we can hand over the problem to Bezos, and we can verify that he did a good job and he did find the correct solution trustlessly. We didn't need to trust him to know that he found the correct solution when he gives us the solution back. Take exact cover, okay? And imagine an insanely large instance. So imagine an extremely large N here, an extremely large M, okay? Millions, billions. If Jeff Bezos solved this instance, he would give us back what? He will give us back a subset T of S. He will say, okay, the solution is S, I, S, J, S, K, etc. This is your solution, Jeff Bezos says. Despite the fact that the problem took probably a month of crunching on AWS to be solved, it would take us seconds to verify that this is true. Why? Well, we just take the union of all of them. Yeah, and the union is very straightforward. The cost of it is linear. If you have a billion sets, it's probably going to take you a billion steps, something like that. Maybe 2 billions, but it's not going to take you 2 to the power of billion. That's the important thing. We just take the union, and then we say, is the union of this equivalent to U? That's all you have to do. And you will know if it's true or false. Same thing for knapsack. If we have to verify the supposed solution that Jeff Bezos told us, what do we have to do? He's going to give us a subset of items. He's going to say the items are item 1, 5, 100, 30, 337, etc. These are the items in the solution. How do we verify? Do we have to search? Do we have to do something fancy to verify the solution? Absolutely not. All we have to do is to add up the weight. We add up the weights and we check, does the weight equal to the imposed C? That's all you have to do. So compared to the solution, which took in the order of 2 to the power number of items, insanely exponential amount of time, it could be larger than the number of atoms in the universe, right? If you have a billion items, imagine 2 to the 1 billion, that's larger than the number of atoms in the universe, many, many times over, obviously. But it will only takes us 1 billion to verify. So this is search. Bezos, this is what Bezos has to do, the amount of work. And this is our verification, which you can do quite easily on any small device. Same thing for the coloring problem. If someone gave us a coloring, what do we have to do? What are we just visit every node and look at its neighbors. Are the neighbors all of different colors or not? If yes, move on to the next one and so on, all the way to the last node. So how many steps does that take? It takes us something in the order of V plus E. The number of vertices, we're going to visit each vertex and we're going to check each of its edges. This is the verification time, the verification work, even though the search was, again, 2 to the order of number of nodes. Same thing for satisfiability. If someone gives us an assignment, all we have to do is go over each node and say each clause, is one of the 3 one in the supposed solution? Check, check, check for each one of the clauses. Okay. And how long does that take us? It takes us at most M operations or 3M operations if we want to check each variable. But you don't have to check all 3 of them because you only need one of them to be true. But in the worst case where the true variable is always the last one in the clause, it takes you about 3 M operations to verify. Okay, compare that to the finding the solution, which is compare that to the solution, which is something in the order of 2 to the power n, because we have n variables and we said there is no way in the general case but to try everything. Okay, so for all of our problems that we saw, satisfiability, coloring, knapsack, exact cover, this is what Bezos would send us after he crunched the solution, after he ran the search on his intergalactic AWS empire. For satisfiability, he gives us a set of tuples. Each tuple is the variable, its index, and the value. Is it 0 or a 1? 3 coloring, it's a set of tuples, okay, and each tuple is a node and its corresponding color. Knapsack, a list of items that should be packed, the list of items that should be included. Exact cover, a list of, or the indices of selected subsets. Which subsets? So these two are, it's basically the same set, the same data structure. The important thing to notice that the data that we receive back, okay, is proportional to the problem size. Okay, we have n variables in satisfiability. We will receive something like n times 2, because it's 2n, because you have the variable and its value. Here, 3 coloring, we have node and color, so it's 2 multiplied by the number of nodes. Knapsack, it's a number, the number of items we receive, it's something less than or equal to the number of items in the instance. Exact cover, same thing. So the data is small. And more importantly, the way we verify that data is true, so this is space or memory, if we're going to fit them into memory. And in terms of, here I'm talking about, data and space. Here I'm talking about search. I am talking about CPU time, okay, is fast or easy. And in all cases, it is proportional to the input size, to the instance size. This is the instance size. Now, compare this, of course, to search, which is something too exponential, something insane. Okay. We do have a name for this data. We have a name for this. We call that a witness. And indeed, it is that very witness that you may have heard of in the zero knowledge context. And we will get back to it later. We will get back to it later, but not before we take a small detour tomorrow to lay down some fundamental ground and then come back and introduce the mother of all reductions and one of the most important results in the history of human thought. I'm talking, of course, about Cook reduction. If you don't know it, don't worry, we'll come back to it. And that reduction should wrap everything together and put everything in perspective. But we will indeed take a small detour tomorrow just to lay down some groundwork and build up to that reduction. But for now, we're coming up on time, so I'll stop here for today. And we will pick up tomorrow at the notion of universality. I'll take any questions if you guys have. Okay, there's a good question from Antonio. I do not understand why the coloring must necessarily translate to satisfiability. Indeed, you are right. We needed to make, well, we would need to make a harder, more rigorous argument about the correspondence between the two. Okay, and we can, if you go back to it. Yeah, if you remember, we it's not like, you know, if you look at the reduction, the papers of the reduction, it's not like you would prove, you would argue with it with syllogism, basically. You would say, if there is ever a coloring, for this graph, these two must have different colors, and those different colors must be something other than blue. Okay, so they must have assumed one of the two. Okay, and then you build up the second argument. Okay, in a valid coloring of this entire graph, these two, each one of them, so they must be different by virtue of this, but they also must be red and green by virtue of that. And then you build up an argument for the clauses, okay, by virtue of, if you build up the truth table of X1, and I encourage you to do this today, later today, if you watch the recording or look at the slides, build up the truth table. Okay, and try to plug it in this gadget. And you will see in the results of the first clause, you will see that it's true, that it's false only when all of the three of them are false. And if either of only one of them is true, it will always be true. So it will be true except in the last case, it will be false only in the first case, and it will be one in all of them. So we can prove that the clause will be, the integrity of the clause will be true by virtue of the truth table. Obviously, we have a node for each variable, so the satisfiability is complete here. So the argument goes something like this. It has a syllogism to it, basically. Yeah, these Matthew asked, oh, these reductions, is this a type of reduction? Yeah, all these reductions that we talked about so far, they are Karp reductions. So what we talked about so far, these are Karp, whoops. What did I do? Sorry, guys. Clicked something by mistake. To answer the question of Matthew, these are what we talked about so far is Karp reductions. If you want to look into more of them, Karp reductions. Tomorrow we're going to look at Gödel and Turing reductions, and then we'll come back to look at Cook reduction. But there is indeed, I think the actual question you probably are asking is, what is common between them? These problems that we talked about so far, they belong to the same class, and we are going back to that class in the last lecture on Monday. So yeah. Am I correct in understanding a zero knowledge proof for 3 coloring is equivalent to a zero knowledge proof for 3 set? Nago, you are absolutely correct, and we'll touch on this on Monday. Yeah, you are absolutely right. Let me see if there are any questions. Vincent says, I just realized on the coloring scheme, when X1 is green and the rest is red, the output will be red. But on the set, when one exists enough to be true, that cannot possibly be, Vincent. And I encourage you to look at the gadget and you work it out and you see that it shouldn't be true. It cannot be true. If one of the three variables that are input to the gadget, it's possible that I messed up something in the presentation, but if you go back here, if one of the three is green, the gadget must necessarily be green. And I encourage you to try out this truth variable, as I said. Truth table, basically. Take every case and see if this could ever be anything other than green. Of course, without doing that, Vincent, without doing that, we already know that this could not possibly be. Well, let me see. This could not possibly be red in any valid coloring because it's connected to this one. So regardless, it cannot possibly be red or blue. It has to be green in a valid coloring, Yeah, you should pay attention to this connection. These are special overall. I think I unplugged something. Okay. This connection is very important. This one is very important to showing you the fact that this could not possibly be anything other than green because they are neighbors. Remember the three coloring requirement. Does this mean, Vishal asks, does all of this mean prover needs, the prover needs to do more computation to prove a statement and verifier needs very less computation to verify? Yes, absolutely. What you are probably hinting at, Vishal, is, or I should say one way of restating what you are asking, Vishal, is, does this mean that these problems there is something fundamental about these problems that allow us to decompose the computation into two parts? Yeah. If we think of a computation as a bucket, this is the amount of resources that you have to expend to solve the problem. Okay. What is fundamental about this problem is that we can decompose the solution into two parts, where this process, you can think of the two part as a prover and verifier, or you can think of it as two processes. And the solution, the final, assurance that the problem has been solved is the combination of the two. And this indeed is big. This is search, and this is verify. So if I understand your intuition, Vishal, it's yeah, I agree with you. This is fundamental to this problem. It's fundamental that their that searching for a solution takes a lot of time and space probably, but verification of a solution that Jeff Bezos gave us takes very little. But it is important to note that this is a property of this class of problems. Basically, we will see touch barely on Monday other classes of problems which do not right away have this easy verification thing, but we can use other tricks to do that. But today the message basically is, this is where this whole decomposition of computation into search and verify into two parts. This is where it came from. Yeah, this is what we call a witness, a certificate that the search has been done correctly, and verifying it is easy. Is easy. I hope I got your intuition correct, Vishal. Okay, going up in the questions. So we answered that. So it looks like we need to be creative on how we create simpler versions of the formula. Okay, so Antonio, I hope I convinced you about the coloring problem. I have convinced you about the, the truth table. You can just write out the truth table. You say, okay, let me try every single one of them and see, verify that indeed all different combination of all the variables in a clause lead to a green, except for the case when all of them are zero. So I would say, Antonio, look at the connections in the graph. Okay, I think that's it in terms of any more questions before we wrap up. Okay, so I guess I'll stop the recording now. Thank you, guys. I will post the slides and the recording as well. I know yesterday I said I'll post yesterday, but I forgot. I'm sorry, but I'll post both yesterday's and today's sessions today. So thanks again, and see you tomorrow.